Hi everyone, I'm Samim and I will be presenting our work titled A Comparative Study of Plug-and-Play and Learning Approaches to Super Resolution in a Real-World Setting. Single-image super resolution techniques, in particular learning-based or learning-supported techniques, have evolved to a point where impressive image improvements can be achieved on a wide variety of scenes. However, their applicability in real-world scenarios is reduced by an often inadequate modeling of the image formation in real imaging systems. To improve on this situation, we make the following contributions in this paper. We generalize PnP optimization techniques for single-image super resolution to handle spatially varying blur kernels. We propose a data synthesis approach for generating realistic input data for deep neural network training that incorporates the major sources of variation in real-world data. We train a state-of-the-art DNN on a suitably synthesized training data set that includes expected real-world image formation variations, that is, varying blur and realistic noise distributions. We experimentally compare the resulting techniques on different scenarios. We find that the end-to-end learning technique yields superior results and robustness as compared to the extended plug-and-play technique, as well as compared against state-of-the-art. In this section, I will explain our proposed generalization of the PnP optimization techniques for single-image super resolution to handle spatially varying blur kernels. Plug-and-play approaches are based on an optimization formulation of the single-image super resolution problem, and to formulate the problem, a forward model of the image formation is assumed. Commonly used model of image formation is given in equation 1, where the observed low-resolution image is denoted by y. It is related to the desired high-resolution image x via blurring, sampling, and addition of noise. The effect of spatially varying blur is modeled by a linear operator h that operates on x, while the sampling of the blurred image is modeled by the linear operator d. The sampled image is degraded by additive noise denoted by n. We switch the order of the blurring and sampling operations. The resulting image formation model, while physically incorrect, is an approximation that enables network-encoded priors to be easily incorporated into proximal optimization algorithms. The resulting optimization problem is given by equation 3, where the first term is the data fidelity term and phi of x is the regularization term encoding the prior information that is network encoded in our setting. Equivalently, the unconstrained optimization problem shown previously can be formulated as a constrained optimization problem given in equation 4 by introducing an intermediate unknown variable z. We use the ADMM method to solve this constrained optimization problem, which involves performing 3 updates iteratively. The first update step is a super resolution scheme with a network-based prior encoded in phi of x, as can be seen by ignoring the dual variable u that tends to 0 as the splitting equality d times x equals z is approached by the iteration. The second update step can be interpreted as a deblurring step at the size of the low-resolution image, which results in an intermediate deblurred low-resolution image z. Previous work considers the blur to be spatially invariant. However, we consider the more general problem with the blur is spatially varying. The third update step is simply the update of the dual variable required in ADMM. We present the details of our approach to solve these subproblems in our paper. The plug-and-play approach has some drawbacks which limit its applicability to real-world super resolution. Prior knowledge of noise level and blur matrix is required, and in some cases, the super resolved images can appear overly smooth because of Gaussian noise assumption. Next, we explain our proposed data synthesis approach to overcome the drawbacks of the PnP method. Our goal is to train a state-of-the-art single-image super-resolution network ESR GAN frequency separation with data that includes variations expected in input data both in terms of realistic noise models, levels, as well as in expected blur variations. To achieve realism, we aim to match the blurring and noise characteristics found in real-world images for the synthesis of low-resolution images on which the network is to be trained. In order to synthesize the low-resolution images, we start off from the DF2K dataset, which is the combination of div2K and flickr2K dataset. It contains around 3000 high-quality images. Since the images can contain residual noise, we clean these images simply by Gaussian filtering and downsampling, resulting in the clean high-resolution image. Let this high-resolution image be denoted by X. The high-resolution image is blurred to obtain a blurred image denoted by X blurred by convolving X with a filter H. The filter H is obtained by randomly selecting one filter from the filter bank. X blurred is then downsampled by the desired scale factor S, giving the downsampled image denoted by Y sub S, where S denotes the factor by which we ultimately wish to super-resolve the images back. The next step consists of injecting realistic noise into Y sub S to finally get the desired low-resolution image. To achieve this, we first convert Y sub S from sRGB to raw space, yielding R sub S. This is in order to apply noise in the linear response regime of the sensor rather than in the non-linearly distorted processed image domain. Next, we generate simulated noise according to the Poisson-Gaussian noise model by sampling from a heteroscedastic Gaussian distribution, which gives us the noise vector n of Rs, and add this noise vector to the downsampled image Y sub S. The last step consists of converting the noisy raw image back into sRGB space, which finally results in the noisy low-resolution sRGB image Y corresponding to the high-resolution image X. With this procedure, we get paired low-resolution and ground truth images for training networks for SR, such that the low-resolution images include variations in expected input data, both in terms of realistic noise models and levels, as well as in expected blur variations. The filter bank consists of 9x9, 7x7, and 5x5 Gaussian filters of different major axes and orientations. A subset of these filters are shown in top left image. We also measure point spread functions of the target optical system by imaging an illuminated pinhole of 30 micrometers diameter in a darkened photographic studio and add these to the filter bank. These are shown in top right image. We also extract blur kernels from real-world images taken with the target optical system using kernel GAN and add them to the filter bank. A subset is shown on the bottom. In this figure, we show examples of synthesized low-resolution, that is blurred and noisy images with different levels of noise obtained by sampling different values of A and B. The parameter A determines the amount of Poisson and B the amount of Gaussian noise components. We generate a variety of images containing different levels of Poisson and Gaussian noise by sampling A and B from a range of values. Experiments. To study and understand the effect of noise on the quality of SR, we perform an experiment in which we synthesize test data only with different noise settings of A and B and study the performance of the different algorithms. Our test candidates are two CNN variants trained with L1 and perceptual loss and PnP method. We train the networks with training data up to the noise parameters A equals 0.03 and B equals 0.025. The figure shows three different performance metrics averaged over 10 test images taken from the validation dataset of div2K. PSNR and SSIM curves refer to the right axis labels of the plots, whereas the perceptual LPIPS metric uses the left axis labels. PSNR is plotted as relative PSNR, which is a fraction of the maximum of 32. The maximum training noise is marked by a dashed black vertical line in the figure. With rising noise levels, the performance decreases for all methods and measures. both for Gaussian and Poissonian noise components. The L1 trained models dominate the PSNR and SSIM scores. In terms of the perceptual LPIP score, the CNN trained with the perceptual loss shows the best performance for low to medium noise levels. This figure shows visual results of one of the test images from our experiment. In the next experiment, we test the importance of modeling the spatially varying blur. For this, we synthesize test images with known spatially varying blur kernels and fix the noise at a specific level. Full details of the experimental setting can be found in our paper. This table shows the numeric performance of each method. We again report averages over 10 test images synthesized with fixed set of kernels. In addition to the previous contestants, we add an L1 trained CNN that was only learned on a spatially invariant kernel to demonstrate the importance of proper modeling. The PnP method is used with known blur kernels. The network trained with a set of blur kernels outperform the network trained on a single invariant kernel, and the PnP method, which operates in a non-blind setting with prior knowledge of noise levels and blur kernels. This figure shows a qualitative comparison of the super-resolved images produced by the PnP approach with the L1 trained CNN. The results from the CNN have sharper details and more realistic textures. We also perform a comparison of our methods with recent state-of-the-art methods for real-world super-resolution on a variety of real-world images taken using different cameras, lenses, and under different settings. The methods we use for comparison are ESR-GAN, which is trained on the default DF2K dataset with clean low-resolution images. We also use the combination of Cycle ISP plus ESR-GAN. Cycle ISP is a state-of-the-art method for real-world denoising, and we use it to clean up the low-resolution images first. Then we use ESR-GAN for super resolution. We also compare against the method of Frisch and others, ESR-GAN frequency separation, which is one of the state-of-the-art methods in real-world super resolution. Since ground truth high-resolution images are not available for these real-world images, we have to rely on a qualitative comparison. The results of this experiment are shown next. ESR-GAN can produce sharp images, however it also enhances the noise and cannot effectively deal with blur in real-world images. The Cycle ISP plus ESR-GAN method, on the other hand, is able to remove some noise, but the resulting images look smooth and lack detailed textures. The results from the ESR-GAN frequency separation are sharp and contain a good amount of detail, however it also enhances noise in parts of the image significantly. For our PnP, we manually tune the blur kernels and noise settings for approximately 1 hour per image and show the best results. As in the synthetic test, the contrast is good but fine detail is smoothed out. Ours ESR-GAN frequency separation produces the best results overall. The noise is effectively suppressed in all parts of the super resolved image. The generated images are sharp and contain a good amount of texture and details. The images from this method are perceptually the most pleasing out of the methods compared. Our experiments show that a single end-to-end CNN for blind single image super resolution trained on a suitably varied dataset can match the performance of a non-blind learning supported optimization algorithm that has full knowledge of both the point spread functions and the noise level. In the perceptually more relevant LPIPS metric, the blind end-to-end network outperforms the optimization algorithm. The PnP optimization scheme can, for our purposes, be interpreted as an upper bound on the performance that a blind learning supported optimization scheme would be able to achieve. The conclusion from our experiments is then that the end-to-end network is more flexible and results in perceptually more meaningful super resolved images. This experimental observation suggests that end-to-end networks are competitive for blind denoising, deblurring, and super resolution tasks.